Good afternoon, class. We are looking at section 4.6, Antiderivatives, part 2. We've already done quite a few problems. So, example 3 continued. We want to integrate the following, the integral of x squared minus 7x plus 2 over x squared. The methodology is similar to differentiation. First, we cut it into 3 fractions. This is 1, which gives you 1. This is minus 7 over x. This is plus 2 over x squared. So we make up 3 fractions first. Now, one by one, we want to make sure they are ready to be going through the process of integration. So this is minus 7 times 1 over x, and this is 2x to the power of negative 2. So number 1, because this is dx, number 1 becomes x minus 7 times 1 over x, which is natural log, so minus 7 natural log of x, 2x to the power of 2 over x squared, or 2x to the power of minus 2. We are going to use the power rule on that. Two divided by negative 2 plus 1, x to the power of negative 2 plus 1. Negative 2 plus 1 is negative 1. We have negative 2 x to the power of negative 1, or negative 2 over x and a constant. Here's the next one. So what do? First and foremost, we notice the independent variable is t, therefore 1 becomes t. Second, the derivative of cosine is negative sign, but the integral is positive sign. So plus sine t plus a constant. Plus sine t plus a constant. The integral of cube root of x minus sine x dx. This one, we write it as x to the power of 1/3, so we can use the power rule on that. So this becomes 1 over 1/3 plus 1, x to the power of 1/3 plus 1. Minus. The derivative of sine is positive cosine, but the integral of sine is negative cosine. So we write minus negative cosine x and a constant. This is 4/3, makes this one 3/4. X to the power of 4/3, and x to the power of 4/3 is cube root of x to the power of 4. This is negative times negative positive, and a constant, and we are done. Now, solve the initial value problems. So the question is, what is an initial value problem? So first and foremost, any equation containing a derivative is called a differential equation, or DE for short. So again, a function which satisfies the equation is called a solution to the differential equation. And what we have been doing in the previous pages is the same thing, solving DE's differential equations. An initial value problem is a differential equation along with a specified value of the unknown function, a pair called the initial condition. So for now, we want to ignore this, and I want to make a point. If you look at this one, dp is the product of these two. And if you integrate both sides, this becomes a p of a t. So let's integrate. And because it's an exponential, remember, in the case of differentiation, we multiply by 3, but integration, we divide by 3, and we add a constant. So it's a very simple integration. And that is the solution to a differential equation. This is the differential equation. This is a solution to it. And this is called a general solution, everybody. The solution is a family of functions. The effect of 3 is that you graph this and it goes up and down along the y-axis. So there are infinitely many solutions. If we didn't have this pair, we would be done. But now that we have the pair, we replace the independent variable happen to be t, sometimes it's x, with 0, and the dependent variable, which is y or p of t, with 1. So 2/3 e to the power of 3 times 0 plus a constant must be 1. E to the power of 3 times 0, this means e to the power of 0, which makes it 1. So this is e to the power of 0 or 1. So you have 2/3 plus a constant is 1. So the constant must be 1/3. You replace this one with the constant, and now you get one solution or particular solution. So without this pair, you have a general solution, you have infinitely many solutions, you have a family of function, and you're done. Adding this, you can find the constant, and it gives you one of those functions. So this is one of those functions, becomes a specific solution, a particular solution. Let's look at another example, everybody. This is also an initial value problem because we are dealing with a differential equation. One pair is given. So for now, we're going to ignore it. And dy means the right side times dx. And y is the integral of the right side. Remember, you need the dx. The integration doesn't mean anything without the dx or dt or d theta. So to integrate this we are not going to touch. This is x to the power of 1/2. Comes up, becomes x to the power of negative 1/2, and we do so because we want to make it ready for integration, anti-differentiation. Well, this is straightforward. This is a natural law. This one, we use the power rule, 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1, and a constant. Believe it or not, this is the only calculus step. So this is ln x. This one is positive 1/2 and makes this one 2. X to the power of negative 1/2 and 1. Positive 1/2 or 2 square root of x. So again, you're looking at a general question, general solution. We have a pair 1, 5. And we are going to plug in to find one of those functions by finding the value of c. So if I replace the x with 1, I get ln 1, which is 0, and this is 2 times 1 is 2. 2 plus what number is 5? C becomes 3, plug it in, and a general question becomes one particular solution. So class, we have infinitely many solutions here, a family of functions. One pair will help us find the solution, a particular solution, one solution. The initial value problem, find capital F of x such that capital F of 2 equals 1 and capital F prime equals 3x squared plus 3x plus 7. Please understand this is dy dx. So what we want to find is capital F of x by integrating this side times dx. All right, we've done this already. Remember, you add 1 to 2 becomes 3, divide 3 by it, you get x cubed. This one, you add 1 to it, 1 becomes 2, so 3 halves x, 3 halves x squared. This is 7x and a constant. Again, that's a general solution. We have the pair 2, 1, which means we're going to replace the x with 2 and f of x or y with 1. 2 cubed is 8, 2 squared is 4, divided by 2, 2 times 3 is 6, 7 times 2 is 14. And so you have 28 plus c equals 1. C becomes negative 27. Replace it. This is an initial value problem solution. So what that means is we have a general solution here because this means infinitely many solutions, a family of functions, and this means just one solution, particular, because we used the initial value that was given to us. Integrate x plus 1 over square root of x dx. We are going to use several algebraic steps and simply one calculus step. So here's what's going to happen. We're going to change the square root of x first. to x to the power 1/2. Then we make up two fractions, x divided by x to the power 1/2 and 1 divided by x to the power 1/2. We use the exponential rule. This has exponent 1. So this becomes x to the power 1 minus 1/2 or x to the power 1/2. This one is x to the power minus 1/2. And all of it is because we want to get it ready to use the power rule. So what happens next? We use the power rule on each case. This one is 1 over 1/2 plus 1, x to the power of 1/2 plus 1. What about this one? 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1. There is nothing else. We add a constant. So this is the only calculus step, everybody. This is it. This was algebra, 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 and now more algebra. 1/2 and 1, they add up to 3 halves. Negative 1/2 and 1, they add up to 1/2. So what's happening here? 1 divided by 3 halves makes it 2/3. 1 divided by 1/2 makes it 2. The final answer is 2 x to the power of 3 halves over 3, or 2/3 x to the power of 3 halves. This is 2x to the power of 1/2 and a constant. Example 7. A sample of cesium-137, which is a radioactive substance, with an initial mass of 79 milligrams, decays T years later at this rate, at the rate of negative 1.8249 e to the power of negative 0.0231 T milligrams per year. Find the mass of the sample after 23 years, rounded to 1 decimal. So let's see what's given. We have the initial mass. We had the rate, which means the derivative, and we want to find the mass. So the very first thing we are going to do, we are going to define the mass as m of t. So we're going to say, let m of t represent the mass of cesium-137 after t years. So that's the first thing. If the rate is this, that means its derivative. That means m prime or dm dt is negative 1.8249 e to the power of negative 0.0231 t, and the initial value means m of 0 is 79. So this is m of 0. This is dm dt. And so what do? We go through the process of anti-differentiation integration to find m of a t in general, and then we just plug in 23. So this part is the easiest part. First find m of t, then plug in. So to do so, we want to integrate this, but we have to put the dt next to it. So m of t is the integral of this piece times dt. To integrate, we are going to divide. Remember, for e to the power of kx, when you differentiate, you multiply by k. When you integrate, you divide by k. So we're going to divide this by the coefficient of t, which is negative 0.0231, and then we write the same thing and a constant. So we divide this number by this number, e to the power of the same thing and a constant. This, you put it into a calculator, gives you 79. Remember, so we found this, but what is this? This is a family of functions. That's a general solution. Now we have this pair, which means replace the t with 0 and y, or in this case, m of t with 79. So this becomes 79. This remains e to the power of any number times 0. This number times 0 is 0. So we get 79 equals 79 e to the power of 0, which is 1. So this is 79 and c becomes u. And so a general solution becomes a particular solution because c is found. So again, I want to make sure we understand this is a general solution. But we wanted a particular solution. And now, after 23 years, replace the t, 79 e to the power of negative 0.0231 times 23, put that into a calculator, raise e to that power, multiply it by 79, and you get the answer, roughly 46.439 milligrams, and then we read 1 decimal. So that means you look at 4, next to it is 3, nothing changes. If it was 5 or larger, this would change. But because next to it is 3, remember, when you want to round, you look at the next decimal. So 46.4, and the units, of course, milligrams. And that's the final answer, everybody.